Okay, good afternoon. Let's continue with our discussions of op-amp circuits. There's only a few more to go, almost at the end for op-amps. So we looked at summing amplifier, basically multiple inputs going into one inverting terminal, and we saw how we can derive the. Oh, let's actually switch over. There you go. How we can derive the output equation and then the gain by taking V out or V in. And if we have the resistor values the same, we can simply say that the total input going into the inverting terminal is simply the sum of the voltages, right? VA plus VB plus VC. Now, this inverting amplifier, what's the gain? Right? Gain is V out or V in. In terms of the derivation, we had minus RF or R1. So if we want a large gain, the ratio of the resistances have to be very large, right? So there are many different configurations of resistors that you can apply in the feedback path. So this is one such configuration. This is also similar to the homework problem. The homework problem has multiple resistors, but the exact same configuration. So let's see how this is an improvement over the standard inverting amplifier. So here, current I1 is going through R1, current I2 going through R2. I3 has been given the direction as going up, and I'll explain why. And then I4, of course, is going towards the output. Okay, so we have established 4 currents through those 4 resistors. Now, when we begin analysis, the first thing we want to check is what kind of feedback, if any, is present in the circuit. So here we take a look at the output terminals. The output terminal is going into the inverting terminal. So it is a negative feedback circuit. It's negative feedback, then it's operating in the linear region. And a lot of your quiz questions will be answered, or at least verified. Right? It's just repeating the same things that we have learned earlier last week. So negative feedback is verified. Then assumption is, of course, that the difference of the voltage going in the 2 terminals is 0. And so is the current I1 or II going into the op-amp terminal, right? So negative feedback, check. Assume V in is equal to 0 and I in also equal to 0. I in this circuit is noted as II. That I, again, is just a subscript of input. Now, the non-inverting terminal is connected to ground. So from the inherent property of a negative feedback op-amp, we can say the inverting terminal is also ground, the virtual short concept, right? Virtual short. So now let's apply simple analysis techniques. I1 is the current that is flowing through R1. Resistor current R1. If you want to describe I1 in terms of the nodes or the node voltages where R1 is connected, what do we have? V in minus 0 divided by R1. And so we simply get V in over R1. Right, we're applying simple circuit analysis techniques. If you remember from node voltage analysis, we can express the resistor voltage VR1 or V1 in terms of the node voltages where the resistor is connected. So we can write it as V in minus 0. V in minus 0 because current's going from left to right. And then, of course, none of the current is going into the op amp. Everything goes through here, through R2. So I can write I2 is equal to I1. And when I2 flows through R2, it causes a voltage drop. Voltage drop will have a plus in the left, which is the point of entry, and minus on the right, which is the point of exit. And this is R3. Now, V1 is connected to that inverting terminal, connected to virtual ground. Right? R1 is connected to the inverting terminal. Right there, which is the virtual ground, 0 volts. So for analysis, you can treat R2 and R3 as in parallel. One more time. From the concept of virtual ground, if the non-inverting terminal is connected to 0 volts, meaning ground, virtual short or virtual ground tells us that we can treat the inverting terminal also as connected to 0 volts or ground. If that's the case, then R3, which is actually physically connected to that same point, and R2, which is connected physically to the inverting terminal, can be considered in parallel, as I've drawn out here. They were already connected here, but now, because of those assumptions for analysis, we can say they share both terminals at their respective ends. So you can consider them to be in parallel. So V1 was plus that way. It's going to be plus here, minus here, and hence you can take I3 as going up through R3. Current always goes from high to low, right? So it goes up from plus to minus. Take 5 seconds. Let me know if anyone has any questions. Yes. A3 section? A3 or R3? I don't understand the question. You're saying, what are you saying? Uh-huh. Yes, it's, well, the voltage across here is plus here, minus here, because you can consider that to be in parallel with R3. The current always goes from plus to minus. For purposes of analysis, again, think back to the first chapter of 201. It does not matter what assumptions you make regarding the voltage polarity or what assumptions you make regarding current directions. It absolutely does not matter. You can take the opposite of logic, opposite of all physical laws, but as long as you're consistent within the problem, your answer will always turn out to be correct. What happens if the answer is opposite of what we assume? Just sign will come out as minus. That's all. So if in the end it turns out that I3 was minus, all it means is I3 is actually going down. That's all it means. But again, if you want to follow logic, then logic dictates that I3 will actually be going up. Once we have I3, we apply KCL at the inverting terminal, we can write expressions for I1, I3, I2, the voltage drops. We can apply KVL from the output all the way back to the feedback path, and we calculate an expression for V out or VO. And then we can calculate the gain. So let's go ahead and do that. Let's see. Where was I? Oh, VR2. So now I'm going to go and continuing to write here on the left. So since I1 is equal to I2, I can write V2. I actually prefer to use the term VR2. Let's use VR2. VR2, the voltage across resistor R2 can be written as I2 times R2. Similarly, VR3 can be written as, so not VR3, I3, the current through there is VR3 over R3. VR3 is equal to VR2. So VR2 over R3, it becomes I2 times R2 over R3. Right, the two resistor voltages are the same. And so it becomes I2 times R2 over R3. Now, I2 is the same as I1, and I1 is equal to V in over R1. So we plug that into this equation, and we get V in times R2 or R1 times R3. We are taking this and we are plugging it in here. Simple plug and result. Yes. Where? Yes. Good catch. VR2. VR1 is actually here. So let me draw it on the diagram itself. VR2. Let's call this VR3. And then this would be VR4. These polarities will be very important when we apply KVL at the end. Does it make sense so far? Right? So now we want to calculate I4. Calculate I4. We can simply apply KCL here because we already know I2, we already know I3. So I4 from KCL, we can write I4 is equal to I2 plus I3. I2 plus I3. Then we plug in the values that we just calculated for I2 and I3. And we can write I2, of course, is the same as I1. I1 is V in over R1. And so it's V in over R1 plus I3, which is V in times R2 or R1 times R3. Yes. 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 Yep. Because of the virtual short at the inverting terminal, we can say the inverting terminal is also held at the virtual ground. And so that renders R2 in parallel with R3. Yeah. That's the important part of that concept. So after that point, it's just straight application of like Ohm's law, KCL, KVL. So now we have V in 1 over R1 plus R2 or R1 times R3. That is our value for I4. No, it will still work. You'll just have a minus sign in there. So if you applied KCL, instead of being I2 plus I3 is equal to I4, we would have it's going out. So it would be I2 is equal to I3 plus I4. So the equation would change. We just have, instead of I2 plus I3, we would have I2 is equal to I3 plus I4 if you had taken it going down. We would say it's minus, right? VR3 would be minus VR2. But it'll still work, except we'd have a minus sign in there. Okay, so far so good. All right. Okay, so then let's turn our attention to the output. We have all our currents. We have I1, we have I2, I3, and I4. So let's look at the output circuit. Output is VO taken from this point, the output of the op amp with respect to ground. Right, RL is connected at the output of the op amp and between ground. So VO is measured with reference to ground. So if you look at just this portion of the circuit, what do we see? Remember, KVL can be applied to any electrical loop. So we can say the output loop, oh, not output loop. Output loop looks like this. This is R4. Oh, sorry, not R4. This is RL. This is R4. This is R3. RL, V out is measured with this reference. R4 has VR4 with polarity plus on the left. VR3 has a polarity plus that way. And if we apply KVL, we obtain the expression VR4, VR3 plus VR4 plus VO is equal to 0. Oh, VR3. And therefore, I can say VO is minus VR3 minus VR4. You can take the minus sign outside and you can say VR3 plus VR4 gives us VO. The minus sign, of course, is because it turns out to be an inverting amplifier. So the output voltage is a sum of resistor voltages 3, R3, and R4. Does that make sense? Output loop. How much time do I have? All right, any questions so far? Yes. Bigger in what sense? Like you mean gain? Yes, we will see that when we finally get the gain equation. So hold on. We're almost there. So now VO is minus I3 times R3 plus I4 times R4. You plug in the values for I3 and R4 in the equation, and we can write VO is equal to, let's see, what is I3? I3 is V in times R2 over R1 times R3 times R3, sorry, and times R3 plus I4. I4 is V in times 1 over R1 plus R2 over R1 times R3. And this is times R4. It's your V out. Okay. Reduce the expression. R3 gets canceled out. Here, let's see, R4, well, doesn't R4 gets multiplied. And so we can have three quantities. V in is common, so you take V in outside, which of course works out because we want to find the gain equation. So we want V out over V in. So you take V in outside, and you get VO is minus V in R2 over R1 plus R4 over R1 plus R2 over R1 times R3. If I take V in on the other side, I get VO over V in, which is my gain equation, is equal to minus R2 plus R4 over R1 plus R2 over R1 times R3. Yes. Where? Oh, this one, R2 times R4. Yes. R2 times R4. I would like to say I'm making these typos on purpose to see who's paying attention, but that wouldn't be true. Yes. So gain is minus R2 plus R4 over R1. So let's take a situation where a standard inverting amplifier, you have R2 and R1, right? Two resistors. If both of them have the same value, like 1 kilo ohm, what is the gain? Just one, right? Minus R2 or R2 or R1. So it's just gain is one. So in this case, if R1 is equal to R2 is equal to R3 is equal to R4, and it's 1 kilo ohm, the gain will be minus, what do we have? 1 plus 1 divided by 1 plus 1 times 1 divided by 1 times 1. So minus 3. So the point is, if you have limited number of resistors in terms of value, if you just have like 1 kilo ohm and 10 quantities of 1 kilo ohm, you can still build a amplifier with reasonable gain. Now, if you had like two resistors with, let's say you had 10 quantities of resistors with only one value each. Let's say 1 kilo ohm and 10 kilo ohms. Gain with a standard configuration would be 10 over 1, a gain of 10. However, if you built the circuit with those same resistors, and let's say we put in R1 equal R3 equal 1 kilo ohm, and R2 equal R4 equals 10 kilo ohms. Now our gain has increased dramatically. So you now have 10 plus 10 divided by 1 and you have 10 times 10 divided by 1. So 120. 10 plus 10 divided by 1, 10 times 10 divided by 1. Yeah, 120. So with only two values of resistances, now you have tremendous gain. If you wanted to just do two resistors, then your maximum gain would just be 10, right? Or if you wanted a high gain like this, you would need to have a ratio of 100 is to 1 or 120 is to 1, which in some cases would not work practically. If you have like a 1 kilo ohm resistor and a 100 kilo ohm resistor in the feedback path, sometimes it might not work for your circuit. So this kind of circuit is especially useful when you want to increase the gain, keeping the same configuration, inverting amplifier, but now you have a very high gain. So one of the homework problems is very similar to this one. You have 3 branches, 3 or 2. You have 2 extra vertical resistors, and you go on solving with the exact same method that I showed here. You don't have to derive everything. It's just a simple question of what the gain would be in that question. Okay. So let's take 10 seconds or more if you need. Think over it. Let me know if you have any questions. Let's recap from the beginning. Yes. Today is what? Monday, right? I hope that students would have started on it already. Some of them have, some of you haven't. So I'll move it back to what, like Thursday? Is Thursday okay? Or do you all want more time? Something, yeah. Yeah, that's correct. Are you, so the due date is there just so that students have enough time. But the assumption always is that as soon as material is covered, students would start solving at least some of the homework, problems in there. Because as you saw in the homework, the homework that was due last night, basically fundamentals that were like short answer questions. And so, those were covered like, quite a few days ahead, like last week. So the assumption would be that students would start solving those and not wait until the last minute to begin solving those. But I will keep it Thursday. Well, do you all need more time? If you wanted to keep on Friday, I will keep it Friday. Show of hands. Anyone wants Thursday? I mean, how many of you are fine with Thursday? How many of you want Friday? 1, 2, 3, 4. Okay, I'll make it Friday. I'll make it Friday, but don't wait until the last minute to begin the homework, right? Most of the material has been covered in advance. So there's no reason to wait until the absolute last moment to actually begin everything, which unfortunately I'm finding myself doing the same thing. So just so much work to get done. I understand. Yes. No, that changes. So inverting amplifier, the input impedance is basically the input current I1, and so it's going to be R1. V equals IR, input voltage is V in, so you have to find I1. I1 is V in over I, gives us R1. So the input impedance for the amplifier, the inverting amplifier circuit, is different from the input impedance of just the pure op-amp. Okay, so everyone, question is being asked, right? What is the input impedance of this circuit? So when you have one final important point before we end class today, when you build a circuit like op-amp, what is the input impedance of an op-amp, ideal op-amp? Infinite, right? When you build a circuit using the op-amp, the input impedance changes. So the inherent properties of an op-amp do not apply if you connect external components. Remember, external components are applying external constraints on the operation of your device. think back to like early chapter 9 diodes, right? When you have external constraints, then the device operation changes. So the input impedance of an op amp is infinite, but the input impedance of a inverting amplifier is simply the resistor R1, right? Yeah. Output impedance is very, very low. Output impedance is very low because in the output equation, there is no mention of RL. So RL could be any value and it does not affect the output at all. So output impedance always stays 0 or very, very low. So again, I want to just make that important point that the op amp properties are different from any circuit that you build with the op amp itself. Okay, so the properties would change because now you have external components that apply external constraints. Hope that makes sense to everyone. All right, I'll extend the homework till Friday. Again, do not wait until the last minute to begin. If you have any questions, please reach out to me. I'll be in my office hours. If you need to see me on Zoom, please send me an email. Okay, do not wait in the meeting.
The reason I asked you is because the homework they're asking, they have that homework asking about like what is the output impedance on a non-inverted non-inverted input section.
Sorry, what?
They have like a question with what is the total impedance on non-inverted
Oh,
input and one for the total impedance of the output
okay.
of the non-inverted. And that one would be
Wait, I need to clear out so the next class can start.